Hey everyone. So today, everyone, so today we are going to solve the score schedule problem from LeetCode. So it's a graph-based algorithm. It's a graph-based question. So we'll set a timer, reset. Sorry, I forgot to reset this. I'm not sure. Like it's been a while that I've done this question and while solving this question, I probably, I looked at in March 16, I solved this question and I looked at a video and probably I don't even remember what this question is about. So let's start. There are, and this is pretty important question. It's been asked in 0 to 6 months. It's pretty much asked at every high level company. So yeah, there are total, there are total of, there are total of there are total of dash like the n courses you have to take labeled 0 to um, the number of courses minus 1. You are given an array prerequisites where prerequisites of I is equal to b ai bi. Okay, indicate that you must take course bi b take course bi first if you want to take course A. For example, the pair 0, 1 indicates that to take course 0, you have to first take course 1. Return true if you can finish all courses, otherwise return false. Number of courses are 2, prerequisites it's 1, 0, true. Number of courses are 2, prerequisites are 0, 1, and both are interdependent on each other. So yeah, in this case, no. So there are total of 2 courses to take. To take course 1, you should have finished course 0, so it is possible. There are total of 2 courses to take. To take course 1, you should have. There are total of n courses you have to take labeled 0 to minus 1. You are given an array prerequisites where prerequisites of I. Okay. So I'm not even sure like how we could solve this problem. So I understand this. Let's reiterate what we understood. So we have given the number of courses that we have to take, and then prerequisites, and we have an array where we have given like it's each item indicates the course and its prerequisite. So we have to um, we have to see through that number of courses at the end is 0, and we can take up the entire courses, okay, and return true if num courses at the end is 0, and return false if num courses does not resolve. So I think I'm not even sure, like I cannot even recall the union find method. So all the pairs prerequisites are unique. Okay, there won't be a repetition, so that would be a nice question to ask. And okay. So my brain is not running at all for this, and it's hint. This problem is equivalent to finding if a cycle exists in a directed graph a cycle exists, no topological ordering exists, and therefore it will be impossible to take all courses. Topological sort via DFS, a great tutorial explaining the basic concept of topological sort. So let's see what this has to be. Basic definition, activity, testing by parties, connectivity in directed graph, tag and topological ordering. Basic definition and application. Graph is equal to vertices and edges, nodes, edges between pairs, captures pairwise. Okay. Finding patterns in corporate chatter. Oh, some graph application, communication, circuit, mechanical, financial, stock currency, transportation, internet, game, board, position, social relationship, person actor, neural network, protein network, molecules. Okay, I guess you should not be heading here. Instead, you go to the LeetCode. This guy explains really well, and let's see what he has to say.
Hey everyone, welcome back. Let's write some more neat code today. So today let's look at a graph problem actually. It's called course schedule. We're given a total number of courses and these are our nodes and they're labeled from 0 to n-1 basically. So some courses have prerequisites. For example, if you want to take course 0, you have to first take course 1 and that's represented as a pair or as an edge in our graph. So if you want to take course 0, you have to first take course 1. And the only question we want to answer is it possible for us to finish every course? So let's just look at the first example. We're given number of courses are 2, so that means we have one course 0 and another course 1. We know that the prerequisites are like this, meaning that if we want to take course 1, we have to first take course 0, and I'm going to represent it as an edge going outward from 1 into 0. So what do they mean by possible? Let's just run through each of our courses and see, is it possible to take each one? So for 0, is it possible to take 0? Well, we don't have any outward edges from 0, so that means 0 does not have any prerequisites. So it is possible for us to complete course 0. Then we look at course 1. It has one prerequisite, which is 0. And we know 0 is possible to complete, so once we finish course 0, then we're allowed to take course 1, which has no other prerequisites, right? The only prerequisite was course 0. So therefore, both of these courses are possible to complete, so we can return true. So let's look at an example where it's actually impossible. So we're given prerequisite was
In this example, it's written that if in order to get course 1, we have to take course 0. So that's why there is an edge, outward edge. Okay.
Was course 0. So therefore, both of these courses are possible to complete, so we can return true. So let's look at an example where it's actually impossible. So we're given n equals 2. That means we have two courses, 0 and 1, and we're given two prerequisites, so 1, 0 and 0, 1. This one means that if we want to finish course 1, we have to first complete course 0. So 0 is a prerequisite. The second one means that if we want to finish course 0, we have to finish course 1 first. So 1 is a prerequisite of 0. So the problem with this is kind of obvious, right? There's a cycle. So if we want to finish course 0, we got to go finish course 1. If we want to finish course 1, we got to finish course 0, and it just goes like that forever. So neither of the courses are possible to finish. So in this case, we return false. So we can actually solve this problem using depth first search. We can also use breadth first search, and I'm going to show you just the depth first search version because I like it better. So given this new example, the first thing you want to do is visualize it. So I'm going to draw a picture. So we're given 5 nodes. So we have 0, 1, 2, 3, 4. That's 5 nodes. We're also given 5 prerequisites. So in this case, we end up having 5 edges, right? From 0 to 1, 0 to 2, 1 to 3, 1 to 4, and 3 to 4. So my goal here is for each of these nodes, I just want to know, right, for each of these classes, can we complete this course or not? And how do we know if a course can be completed? Well, just looking at this picture, it's obvious, right? 0 has a prerequisite of 2, but 2 does not have any prerequisites, which is great. It also has a prerequisite of 1, and 1 has 2 prerequisites, 3 and 4. 3 has 1 prerequisite of 4, and 4, luckily for us, does not have any prerequisites. So looking at this, the structure I'm going to use is a hash map to represent this. So for each of our courses, we are going to have a list of all of its prerequisites. So for 0, we know 0 has 2 prerequisites, 1 and 2. And we're going to repeat that for every single course. So for 1, we know that 2 does not have any prerequisites, so we can just put an empty list over here. 4 also does not have any prerequisites, so we get another empty list. So now we're going to run depth first search on every single node. I'm going to do it in the order from 0 to n minus 1. So be starting at 0, so we're going to run depth first search on it, right? How are we going to do the depth first search? Well, we have our prerequisite map, so we're going to do it recursively. We see that it has 2 prerequisites, 1 and 2. So now let's run depth first search on the first neighbor 1. So now we look at 1, we see that it has 2 neighbors, 3 and 4. So let's recursively run depth first search on its first neighbor 3. So since 3 is a prerequisite of 1, now we want to know if we can complete course 3. So we look at its prerequisites. It only has 1, 4. So now we're going to check its only prerequisite 4. Can we complete course 4? And then we want to look at the prerequisites of course 4, which we know are empty. This is good, right? So now we see that this is empty. So what does that tell us? That tells us course 4 can be completed, which we basically already knew because course 4 has an empty prerequisite list. So I'm just going to put a little check mark here to say that we know course 4 can be completed. And so recursively, we're going to end up going back to our 3, and we see that it only had 1 prerequisite, and we were able to complete that prerequisite 4. So therefore, 3 is also a course that can be completed. And so what we can actually do is from its prerequisite, and so recursive, what does that tell us? That tells us course 4 can be completed, which we basically already knew because course 4 has an empty prerequisite list. So I'm just going to put a little check mark here to say that we know course 4 can be completed. And so recursively, we're going to end up going back to our 3, and we see that it only had one prerequisite, and we were able to complete that prerequisite 4. So therefore, 3 is also a course that can be completed. And so what we can actually do is, from its prerequisite list, we see 4, we can just remove the 4. We know it can be completed. And so I'm representing that by having an empty list here, right? Just an empty list means that it has no prerequisites, therefore it can be completed. So I removed the only prerequisite that 3 had. Then from 3, we can actually go backwards to 1, which we see here. We can kind of get rid of this 3 because we know 3 can be completed. And then from the 3, we're going to end up going to 4 to check again if 4 can be completed because it is a prerequisite of 1. And since we already know 4 can be completed, we can get rid of that as well. So now we know for sure that 1 can also be completed. And now I'm going to go back to 0, which is how we even got to 1 in the first place. And we look at the prerequisites of 0. We see 1 is no longer a prerequisite because we basically know that 1 can be completed, but we still have to look at this 2. So then we're going to go to the last unvisited node in our entire graph, which is 2. So now we've gotten to the last course 2. We see it's an empty list, right? Therefore, 2 can be completed. It has no neighbors. It has no prerequisites. So I can put a little check mark here. 2 can be completed. And then we can finally go back to our original node, 0, cross out its last prerequisite, which was 2. And now when we look at 0, even 0 has an empty list of prerequisites. Therefore, we know 0 can be completed. So since we were able to complete every single course, that means we can return true. Every course is completable, and the time complexity for this is going to be big O, the number of nodes we have, which is n. I'll use n as that, and I'll use p for the number of prerequisites that we had, because if you notice in this graph, we have to visit every single node, and we have to move along every single edge. And once we get rid of the prerequisites from here, we don't really have to visit a course twice, because once we know it can be completed, we can instantly do that. We don't have to go through its prerequisites twice. So I'm going to show you one last example. This is the example that what we're going to do. How are we actually going to detect this loop? Because we see, so I'm just going to cross this stuff out because we're looking at a different example. But here we see that 0 has a prerequisite of 1, 1 has a prereq of 2, 2 has a prereq of 3. So this is a loop. We cannot complete these courses, but how can we actually detect this loop? I'm going to show you how really quickly. So to detect a loop, I'm going to use one last data structure, and it's going to be a set. Though I think you could just use an array if you want. I'm going to call it the visit set. And all it's going to contain is the list of courses that we're currently visiting along our depth first search. So let's say we start at 0, then we add 0 to our visit set. We take a look at the prerequisites of 0. We see it has one prerequisite. So then we move to 1. So now we visit 1. So we're going to add 1 to our visit set. And we look at the prerequisites of 1. It has one prerequisite 2. So then we move to 2. We run depth first search on 2. So to do that, we have to first visit 2. So 2 is also going to be added to our visit set. And lastly, we see 2 has one prerequisite of 0. So then we, of course, want to visit 0. And so now we're going to visit 0 twice, but you see that 0 is already in the visit set. Therefore, we detected a loop. Therefore, we have to return false. These courses cannot be completed. So now let's finally look at the code. So the first thing I want to do is create our pre-map. So our list of prerequisites. So we know for each course, initially we can set it to an empty list. So an empty list of prerequisites. And we want to do that for every course that we got, which the number of that is just number of courses. So this is, if you're not familiar, this is some Python stuff. I'm just saying that for every course initially, we want to map it to an empty list. And we know that the prerequisites are actually contained in this nested list variable. So let's iterate through that. Let's get each course prerequisite pair from that list and then just start appending them. So pre-map of course, we want to append to this list this prerequisite. So we also want a visit set, which is going to store all the courses along the current depth first search path. And of course, it's initially just going to be empty. So since we're going to do this recursively, I'm going to define a nested function, depth first search, inside of our canFinish function, because then we'll have access to all these variables without having to pass them in as a parameter. The only parameter that we have to pass in is the current course that we're visiting. And so like most recursive functions, we want to look at our base cases first. The first base case is if course is in the visit set already. So what this means is that we're visiting a course twice. So we detected a loop, so we can return false, meaning that this course cannot be completed. The other base case we know is if the prerequisites of this course happen to be an empty list. What that tells us is that this course has no prerequisites, and we can return true because it can definitely be completed. If neither of these conditions is satisfied, then we can take this course and add it to our visit set, because that means we are currently visiting this and we're going to recursively run depth first search on its prerequisite. So I'm going to loop through the prerequisites of this course. For each one, I'm going to run depth first search on it. So depth first search on this prerequisite. If it happens to return false though, then we know we can return false immediately. We don't have to wait, because if we find one course that can't be completed, then we can return false for the entire function. So I forgot to put a not over here. So if not, meaning if it returns false, then we return false. But if this does not execute, that means it's a course that can be taken, and we want to return true in that case. But before we return true, we want to remove it from our visit set, because we are no longer visiting this. We've already finished visiting it. So visit, remove this course. And also, since we know this course can be visited, what we can do is say pre-map. We can set it to an empty list, so that if we ever have to run depth first search on it again, we will, in that case, execute this condition and return true immediately. We will not have to repeat all this work of running depth first search on its neighbors. So that's all for our depth first search function. The function is done. All we have to do is call it now, but we have to potentially call it for every single course in the number of courses that we have. And if any of them happen to return false, then we have to return false immediately. And if they don't return false, then we can return true. All courses can be completed. And the reason we are looping like this is mainly because what if our graph is not fully connected? Like, what if we have a graph like this? One has a prerequisite of 2, and maybe 3 has a prerequisite of 4. So these are two separate graphs that are not connected, right? So we have to manually iterate through every course and check, can 1 be completed, can 2 be completed, can 3, and can 4 be completed. So this is the depth first search solution. You can see that it does run very efficiently, about as efficiently as the breadth first search solution as well. And I hope this was helpful. If it was,
Okay, so after going through the solution, I'm pretty confident that I understood it. Uh, so for practice sake, I'll just go through this once. Okay. So yeah, once once we have this, then we can uh, see this example. The example that was shown on LeetCode was something like how do we start this? Okay. Okay, there's a problem in here. Okay. So basically what we are doing, that adjacency list, to create the adjacency list data structure, we are using a map. Let map is equal to new map, and then what we have to do is number of courses are given. So number of courses are labeled from 0 to -1. So for let I is equal to 0, I is less than number of courses I plus plus. What we have to do is we have to map dot set 0 with this guy, right? Oh no, not 0, actually I with this guy, and then yeah, we should put, and then we have to again loop through let I is equal to 0 eyes, or let course and prereq, let's call it prereq of prerequisites. So map dot set course like how can you do it efficiently? I'm just trying to see that. Oh, you don't have to set it again. You have to just get course dot push the rec. Once you do that, then you have to run a function tfs which takes in a course. Once you take in the course, and you have to also let visitor is equal to new set. So once you have this set, you have to check if visited dot has course, then you will return false if prereq. Okay, so if visited has course, then return false. Okay, so if visited has course return false, and then maybe at this point I'm just uh, mugging this code up. Uh, okay, if visited course is there, so here what I've done is okay, yeah, this is good. This array, using this array. Okay, visited course, then return false. If map.get course equal to null, then return true. Okay, it's pretty simple solution, but yeah. Let course is equal to let's say let's visited is equal to new array. Let's take array of size num courses dot fill with uh, false first. Visited, and let's get rid of this guy, and if map dot get course equal to the array, then return, that means nothing has to be traversed, then return false. Then for let prereq of map dot get course if dfs, if not, like if it doesn't return true, then we'll return false, or else so we are visiting this node, right? Visiting visited of course equal to true, and then once we are done with this, visited of course equal to false, and then um, map dot set, so that, so once we have visited everything in a course, we have to set that course to empty, then return true for that. Okay, so once we have done that, then um, we have to also run it for let I equal to 0 is less than num of courses I plus plus, then map dot get, sorry, DFS if not DFS I return false, else return true. Okay, so yeah, was- so this is pretty difficult question to wrap your head around. I would surely come back to this question in few more days, but yeah, I need to revise this question again and try to solve it again. So the time complexity. So how did they solve it with topological sorting using Khan's algorithm? They used topological sort. I'm not even sure what's that. Okay, so this was the basic DFS approach. So initializing of m adjacent times as we go through all the edges, initializing the visit and okay, this was a pretty bad session. I need to um, see through where I was lacking and get back and solve this question again. Cool. No worries. We'll be striving hard next time. So that is it. Well, so 38 minutes I've spent on this. So okay, cool. No worries. Next time it is.